We end tonight with the clearest pictures yet of Neptune, the most distant planet in our solar system. Take a look. The striking infrared images were taken this summer by the James Webb Space Telescope.
Something massive just happened at the edge of our solar system, and it's sending shockwaves through the scientific community. The James Webb Space Telescope, humanity's most powerful eye in the cosmos, has reportedly captured something no one ever expected: an enormous, unidentified object colliding with Neptune. Was this a natural cosmic event? Or is there something far more mysterious unfolding right before our eyes? In this video, we'll uncover the secrets behind this amazing discovery and what NASA isn't telling us about this shocking Neptune collision. But before we dive deeper into this mystery, make sure to hit that like button and subscribe, because what you're about to see will change the way you look at our universe forever. Neptune has long been a planet shrouded in mystery. Despite being the fourth largest planet in the solar system, its distance and faintness have kept it relatively unexplored. The Voyager 2 flyby in 1989 gave humanity its first close look, revealing turbulent winds, immense storms, and a deep blue hue born from methane in its atmosphere. Since then, astronomers have relied on ground-based telescopes and, more recently, the Webb Telescope to track its weather patterns and study its faint rings and moons. But never before has humanity witnessed a direct collision on Neptune itself. Until now. The Webb data revealed not only a sudden burst of heat rising through the atmosphere, but also chemical fingerprints suggesting that foreign material had been injected into the planet's skies. The residue of a wandering object that met its end against the immense gravity of the ice giant. To understand the magnitude of such a collision, it helps to picture the size and scale of Neptune. With a diameter almost 4 times that of Earth and a mass 17 times greater, its gravitational field dominates its corner of the solar system. An object large enough to leave a visible mark on such a planet is not a small asteroid, but something far more substantial. The Webb data indicated the intruder could have been a body tens or even hundreds of kilometers across, possibly a rogue icy object from the Kuiper Belt, or a stray comet dislodged from the solar system's outermost reservoirs. The sheer violence of its impact, though absorbed by Neptune's thick atmosphere, must have released energy on a scale impossible to truly grasp, rivaling millions of nuclear explosions unfolding simultaneously. The collision itself would not have looked like the familiar fiery impact we associate with rocky planets such as Earth or Mars. Neptune's atmosphere, composed primarily of hydrogen, helium, and methane, is a dense, shifting ocean of gas and ice particles. As the object plunged inward, it would have compressed the atmosphere in front of it, creating shockwaves that spread outward at supersonic speeds. Instead of cratering the surface, because Neptune lacks a solid surface in the conventional sense, the intruder would have dissolved and fragmented, injecting its own material into the swirling hydrogen seas. Webb detected sudden enhancements in carbon-based molecules and unusual spectral lines that hinted at exotic ices, possibly ammonia or carbon dioxide, that had been carried in by the foreign body. This chemical scar may persist in Neptune's atmosphere for decades, a lingering testament to a brief but monumental encounter. One of the most remarkable aspects of this detection is that it underscores the dynamic and hazardous nature of the outer solar system. For decades, Neptune has seemed a distant and tranquil world, serenely orbiting far from the chaos of the asteroid belt and the storms of Jupiter. Yet the Webb telescope has revealed that even here, nearly 3 billion miles from the Sun, collisions still occur. The solar system remains an active, evolving place where icy wanderers travel on unstable orbits and occasionally plunge into the grasp of the giant planets. What Webb witnessed was not a relic of the solar system's violent formation, but a contemporary event, a reminder that planetary impacts are not just ancient history, but an ongoing reality. The implications extend far beyond Neptune itself. Observing such a collision allows astronomers to refine their understanding of how impacts shape planets, both in our solar system and beyond. Impacts are a fundamental driver of planetary evolution. They deliver volatile compounds, stir atmospheres, alter orbits, and sometimes even strip planets of their outer layers. On Earth, impacts have reset the course of life more than once, from the asteroid that ended the reign of the dinosaurs to earlier collisions that may have brought water and organic molecules to the young planet. On gas and ice giants, the role of impacts is less well understood because the lack of a solid surface makes direct evidence harder to find. But Webb's detection of this event gives scientists a rare chance to study what happens when a massive object plunges into a gaseous planet, a scenario that may be common in exoplanetary systems across the galaxy. The energy released by the collision would have penetrated deep into Neptune's layers, potentially disturbing its atmospheric circulation. Neptune is already known for its ferocious winds, which can reach speeds exceeding 1,500 miles per hour. The injection of heat and momentum from the impact could have stirred these winds into even more chaotic motion, generating temporary vortices or enhancing existing storms. Indeed, Webb's subsequent images revealed unusual bright spots and disturbances in Neptune's cloud bands, structures that seem to rotate and elongate in patterns unlike the familiar storms tracked in recent years. These may represent the atmospheric echo of the impact, fleeting structures sculpted by the turbulence unleashed in that cosmic collision. For planetary scientists, the chemical aftermath is the real treasure. Webb's instruments can split light into astonishingly fine detail, making it possible to detect molecules at parts per billion levels. Spotting unusual compounds in Neptune's upper atmosphere hints that the impactor delivered rare materials straight into the planet. By analyzing these chemical fingerprints, scientists can uncover the composition of the colliding body, turning Neptune itself into a natural laboratory for examining matter from the farthest corners of the solar system. If the object originated in the Kuiper Belt, its chemistry may act as a time capsule from the early solar system, a preserved fragment of the primordial disk that once gave rise to the planets. By colliding with Neptune, the object has ironically become much easier to study, its contents scattered and glowing in infrared light beneath Webb's powerful gaze. The rarity of catching such an event makes it even more remarkable. Collisions on Neptune are believed to happen, but usually on timescales stretching from centuries to millennia. The fact that Webb was watching at exactly the right moment shows its extraordinary value as a cosmic sentinel. Unlike telescopes on Earth, which struggle to see clearly through our atmosphere, Webb's position in deep space lets it capture brief, fragile events in sharp detail. It is not just a machine for exploring faraway galaxies, but also a watchful guardian of our own cosmic neighborhood. This discovery highlights its unmatched versatility and teases the many surprises it may still uncover as it continues to keep an eye on the planets. The impact also sparks fascinating questions about Neptune's role as a gravitational gatekeeper of the outer solar system. Sitting just inside the Kuiper Belt, a sprawling region of icy leftovers from planetary formation, Neptune has shaped the orbits of countless objects for billions of years. Its gravity traps some bodies in resonant patterns while flinging others out into interstellar space. The collision Webb detected may well be the result of this gravitational power. By nudging an object inward, Neptune may have signed its own target, struck by the very body it destabilized. The event is a powerful reminder that planets and smaller bodies are bound together in an endless gravitational dance, constantly influencing one another with subtle pulls and, at times, dramatic and violent encounters. For scientists studying exoplanets, Neptune's collision offers a striking parallel. Many planets discovered around distant stars are gas and ice giants much like Neptune, orbiting far from their suns. The forces shaping those alien worlds are likely similar to the ones at work in our own solar system. By watching a collision unfold on Neptune in real time, astronomers gain a rare window into processes that could also occur on these faraway giants. Events that might reshape atmospheres, ignite storms, or even affect whether their moons could sustain life. Webb, with its ability to analyze exoplanet atmospheres as precisely as it did Neptune's, can now use the lessons from this event to decode signals from other systems. Every spectral signature, every chemical trace revealed on Neptune becomes a vital clue for understanding worlds scattered across light years of space. The impact also carries weighty implications for planetary defense. Earth is protected from many incoming objects by the immense gravity of Jupiter and Saturn, but Neptune's collision shows that impacts remain a fundamental part of the solar system's rhythm. Watching Neptune absorb such a massive strike is both a sobering warning and a reassuring reminder. It demonstrates the sheer destructive force of wandering objects that cross planetary paths, yet it also highlights the role of giant planets as cosmic shields, pulling in or redirecting debris that might otherwise endanger the inner worlds. In a sense, Neptune's collision is a testament to the silent guardianship of the giants, whose gravitational influence has helped ensure that Earth remains relatively safe. Even as scientists examine Webb's vast troves of data, new puzzles are already emerging. Some of the chemical features spotted do not neatly match any known compounds, hinting that strange, unfamiliar reactions may have taken place when the impactor's materials mingled with Neptune's unusual atmosphere. Such reactions could generate exotic molecules seldom seen elsewhere, opening fresh paths of exploration for astrochemists. The lingering thermal glow Webb detected was also surprising. It lasted longer than expected, suggesting that the impact's energy burrowed deeper than models predicted, perhaps reaching Neptune's mysterious inner layers. These inner zones may harbor exotic forms of matter, such as superionic water and unusual ices crushed under immense pressures. Probing these signs could bring us closer to solving one of the biggest mysteries about ice giants. What truly lies beneath their restless skies? And how do their interiors change with time? The collision recorded by Webb is more than a singular flash of cosmic drama. It's part of a much broader story of planetary evolution and cosmic connection. Neptune, long regarded as a distant and largely static world, has proven itself to be a stage for intense encounters that remind us the solar system is far from quiet. By capturing this rare event, Webb transformed a distant possibility into a vivid reality, giving humanity front-row access to one of the universe's most fundamental forces. Collisions build planets, transform them, and sometimes destroy them. They are destructive yet creative, erasing old forms while sowing the seeds of new ones. In the violent meeting of a wandering object and a massive planet, we glimpse the same forces that shaped Earth and continue to sculpt the cosmos. This discovery will echo in science for years, not just as a record of Neptune's encounter, but as a glimpse into countless unseen impacts happening across the galaxy. For every collision we manage to witness, countless others play out unnoticed in the vast dark. Thanks to Webb's remarkable vision, one of these hidden events has been unveiled, giving us a rare chance to watch the raw mechanics of planetary change in action. Neptune's collision is both a revelation and an invitation, a vivid reminder that the universe is alive with motion, and that even the most remote worlds continue writing their stories in fire and ice. Webb's discovery of a massive impact on Neptune is not just a spectacle, it is the opening chapter in a deeper investigation. To truly understand what this event means, one must look beyond the flash of the collision itself and consider Neptune's environment, its delicate web of moons and rings, and the broader astrophysical questions sparked by watching a giant planet struck in real time. Each of these threads expands the story, sharpening our view not only of Neptune, but also of the intricate dynamics that hold the solar system together. Compared with the grandeur of Jupiter or Saturn, Neptune often fades into the background, yet it harbors mysteries all its own. Unlike Jupiter's bold cloud belts or Saturn's dazzling rings, Neptune presents a quieter profile. Thin arcs of rings and an atmosphere both dynamic and secretive. Into this subdued world came the enormous intruder Webb detected, and the effects radiate outward to everything bound by Neptune's gravity. Its 14 known moons, led by the enigmatic Triton, may have experienced subtle shifts in their orbits in the aftermath. Though most of the impact's energy was swallowed by Neptune's thick gaseous envelope, the redistribution of heat and mass could, over time, alter its gravitational field in minute ways. These changes might be too faint to measure immediately, but across centuries they could prove meaningful. For scientists, this presents a rare chance to track Neptune's moons with new precision and to test whether impacts can leave measurable imprints on the architecture of planetary systems. Triton, in particular, deserves the spotlight. Larger than Pluto and thought to be a captured Kuiper Belt object, Triton carries the scars of its dramatic past. Its retrograde orbit reveals it as an outsider long ago ensnared by Neptune's gravity. In many respects, the recent collision observed by Webb mirrors this ancient drama on a smaller scale. Another wanderer drawn into Neptune's grasp. Triton itself is geologically restless, with nitrogen geysers bursting from its surface. Perhaps disturbances from past impacts linger in its chemistry or orbital record, marking echoes of Neptune's ongoing encounters with roaming bodies. If so, Webb's observation is more than a single event. It is a continuation of the same forces that billions of years ago reshaped Neptune's family of moons. It reinforces the idea that collisions are not confined to the solar system's birth, but remain a persistent and active agent in sculpting planetary systems. Neptune's rings also enter this unfolding story. Though faint and fragile compared to Saturn's majestic system, they are mysterious arcs of dust that seem to shift, fade, and reform with time. A colossal impact could easily send fresh material into orbit, altering or replenishing these delicate structures. Webb's sensitive infrared instruments may soon detect new populations of dust or brightened arcs, the silent debris left behind by the intruder. This raises a broader question. How many ring systems across the solar system were born or refreshed by the violence of impacts? Saturn's rings may be iconic, but they might not be unique in having a catastrophic origin. The faint arcs of Neptune could be a reminder that destruction and creation are forever intertwined, and that even the most fragile structures in space may be written into existence by cosmic collisions. Neptune's recent collision offers a live case study for testing the connection between impacts and ring dynamics. From an astrophysical perspective, what happened at Neptune also resonates with theories about planetary system stability. The outer solar system is not a static place. It is influenced by resonances, gravitational scattering, and long-term orbital migrations. The very existence of the Kuiper Belt testifies to this, as does the presence of extreme trans-Neptunian objects whose orbits hint at past upheavals. A massive body striking Neptune is more than just chance. It suggests a chain of gravitational nudges stretching across the solar system, a subtle choreography that guided the impactor inward. Scientists studying orbital mechanics will look to model how such an object could have been delivered to Neptune's path, whether by resonance interactions with Neptune itself, long-term perturbations from passing stars, or chaotic scattering within the distant Oort cloud. In this way, the collision is not just a planetary event, but a window into the deep dynamics that keep the solar system in motion. The energy of the impact also raises profound questions about Neptune's interior. While we often picture gas and ice giants as uniform spheres of hydrogen and methane, their insides are far stranger. Beneath Neptune's atmosphere lies a mantle of water, ammonia, and methane in exotic states. Superionic water that behaves like both liquid and crystal. Ices that conduct electricity under immense pressure, and layers that generate Neptune's bizarre tilted magnetic field. A collision of the magnitude Webb observed could have penetrated these layers, disturbing convection currents or triggering unusual mixing. Though we cannot see these depths directly, the aftermath may be traced in changes to Neptune's magnetic field, auroras, or thermal emission. Already Neptune is known to radiate more heat than it receives from the Sun, suggesting internal energy sources that remain poorly understood. By perturbing this system, the impact may have provided a natural experiment in planetary physics, temporarily altering heat flows and magnetic structures in ways that can be studied as Webb continues its observations. Exoplanet science gains new dimensions from this event as well. Astronomers have catalogued thousands of worlds orbiting other stars, many of them ice and gas giants resembling Neptune in mass and size. Yet the details of their atmospheres and evolution remain obscure. One of the challenges in exoplanet studies is understanding the role of stochastic events, rare but powerful processes like collisions, in shaping planetary appearances. A hot Neptune observed in another system might display spectral signatures or atmospheric anomalies that result from an impact long past. Without a reference in our own solar system, such anomalies might remain mysterious. Now, with Webb's detection of a Neptune collision, scientists can build a library of impact fingerprints. Sudden chemical enrichments, irregular heat emissions, or transient cloud formations. These can be used to interpret data from distant worlds, bridging the gap between theory and observation. On a more speculative front, the impact on Neptune also highlights the possibility of cascading effects through the outer solar system. Neptune shares its domain with countless icy bodies in resonant orbits, many of which are stabilized by its gravity. If an impactor was drawn from this population, others may follow similar pathways in the distant future. Could Neptune experience multiple collisions over cosmic timescales, gradually accumulating material from the very region it shepherds? This cycle of capture, collision, and assimilation might even contribute to Neptune's anomalous properties, such as its unexpectedly strong winds or peculiar thermal balance. Each impact could serve as a tiny nudge to the planet's evolution, invisible on human timescales, but decisive over billions of years. The Webb Telescope's glimpse of a monumental collision on Neptune did more than spotlight a planetary drama. It cast a wide net of implications across science and human curiosity. With every new layer of inquiry, new perspectives emerge, and each angle sheds light on facets of Neptune, the solar system, and the universe at large that often remain hidden. Expanding further into the event and its meaning allows us to step into speculative yet scientifically grounded territory. The potential effects on Neptune's lesser-known moons, the analogies this offers to ancient planetary formation, the lessons it teaches us about habitability in harsh environments, and even how it could influence the way humanity organizes its priorities for space exploration. One intriguing area of study is Neptune's smaller moons. While Triton commands the spotlight with its size and retrograde orbit, Neptune also hosts numerous tiny, irregular satellites, many of which are barely resolved even with modern telescopes. These moons are thought to be captured objects from the Kuiper Belt, fragile wanderers bound by Neptune's pull. The shock of a major collision with Neptune could subtly alter their orbital alignments, or even perturb their surfaces with showers of secondary debris ejected during the event. Some of the faintest moons are little more than ice and rock conglomerates, only a few tens of kilometers wide. If material from the collision was cast outward into a temporary orbit before falling back into Neptune, these moons could have intercepted some of it, creating fresh craters or layering their surfaces with exotic compounds from the impactor. In a sense, the moons could serve as natural archives of the event, their icy shells holding records of particles that once blazed through Neptune's skies. If you enjoyed this video, don't forget to hit the like button and subscribe to our channel for more space discoveries and cosmic stories. We'd also love to hear from you. Share your thoughts in the comments below. Do you think Neptune's collision was just a natural cosmic event, or could there be something more mysterious behind it? Your perspective matters, and we can't wait to read it. Thanks for watching, and we'll see you in the next video.